Alright guys, so today I'm going to talk about transforming exponential functions. So I put together this little presentation. We're going to go over a couple examples, and we're going to review some transformations in general, and then what that looks like with exponentials, and some examples and stuff, right? So, transforming an exponential function follows along with our transformations that we studied way back when. That is our a f of bx plus c plus d, right? Just doing the same things we did then, now to our exponential graph. Okay, so first, transforming bx plus c. Please note that Please note that with transforming bx plus c, these are the domain transformations. Remember, we go inverse the order of operations. We go backwards. We're going to transform with c first, and then b second, right? It was just like when we set up and solved equations, where we would transform a point, right? We would take an old point a comma b, and we would transform it with our domain transformations. And the way we always solved it was setting that bx plus c equal to a, and then solving for our new value. And how did we do that? We subtracted c first, which is why I say we do c first. Also, we subtracted c, which means the point moves in the opposite direction of what c is. So if you see c being a plus 3, we know that would go to the left. If c was a minus 3, we knew it goes to the right, and so on. Okay? And then, of course, the second transformation that we do here is our horizontal stretch and compress. And so we would say that c is going to shift the graph left and right. C comes first. If c is positive, it goes in the negative direction. It's actually going to shift it to the left if c is positive. And if c is negative, it's going to shift the graph to the right. Okay? B stretches or compresses horizontally greater than b. Of course, remember that b divides the x's. All right, and so if b is a large number, when you divide, it's going to compress towards the y-axis. Points on the left and right are going to be compressed inwards, whereas if b is a fraction, it's going to stretch away from the y-axis. Our range transformations were much easier, much more natural. We do the order that we see. We do the operations that we see. All right, we would take the old range value and just multiply by a and then add d. It was very, very much easier and more what you would expect. And so we would first transform by a, second transform by d. If a is greater than 1, we're going to stretch it away from the x-axis. So points would be stretched up or stretched down. If a is a small fraction, like a half, that is, you're going to take half of all your y values. Remember, range is the y's. That's going to push and compress things towards the x-axis. And then finally, d just goes ahead and shifts graphs up and down. So now how does this look with exponentials? We have f of x equals a times b to the bx plus c plus d. Please note that b is just our base, and it determines how steep and whether our graph is increasing or decreasing. So, we did this in a previous video. 2 to the x, we know, is just a nice increasing exponential function, whereas 1/2 to the x is the same thing as 2 to the negative x. This is a decreasing exponential function. Okay, both of them go through the y-intercept at 0, 1. Both of them have a horizontal asymptote along the x-axis. Of course, if our exponent, or our base rather, gets bigger, like 3 to the x or so on, 3 to the x would just be steeper on the left over here, and below, or steeper on the right rather, and below on the left. So 3 to the x would be something like that. Sorry for my horrible hand drawings. All right, you'll see better graphs. So now some simple examples, right? E to the x minus 2. Please note, e is the natural number. It's just an infinitely long, never-ending, never-repeating decimal. It is a beautiful number. We use it a lot in mathematics. It is about 2.718, and so on. It keeps going on, you know. So really, it's a base that's in between 2 and 3. It's just our exponential, and regular old e to the x, all right, has all the features of an increasing exponential function going through 0, 1. Okay, so now e to the x minus 2 plus 3, the minus 2, of course, shifts it to the right 2, and the plus 3 tells us to go up 3. So we have our horizontal asymptote. Instead of at 0, that's been shifted up. Remember, when you move your graph, your asymptote shall follow. The point 0, 1 has gone up. It's now going to be at 4, but because we've shifted the graph to the right 2, that point, that strategic point that was our old y-intercept, is now going to be at 2, 4. All right, so horizontal asymptote at 3, strategic point at 2, 4. Pretty easy example. Just shifting to the right. This is up in the domain, shifts right and left, changes our x values, and the plus 3 here changes our y values. Good. Another example, 3 to the x. This base doesn't really change much. It's just a little bit steeper than 2 to the x. Please note, this plus 3 here means left 3, and the minus 2 means down 2. So we have our horizontal asymptote at y equals negative 2. We're going to have our strategic point, instead of at 0, 1, it's now down at negative 1, and to the left, so it's negative 3, negative 1 is where our strategic point ends up. Okay. Some reflections, 2 to the negative x. Of course, we know that this is the same exact thing as 1/2 to the x. This is just a decreasing exponential function. It flips it over the y-axis. We still go through 0, 1. And of course, the original 2 to the x would probably look something, I'll do this in gray. The original 2 to the x would look something like that. Okay, that would be 2 to the x. All right. Second reflection, the negative out in front flips us over the x-axis. We now have our y-intercept at 0, negative 1 instead of positive 1, and we still have our horizontal asymptote at y equals 0. So that's a reflection over the x and a reflection over the y. Now, here I went ahead and graphed and compared a vertical stretch versus a horizontal compression, right? So the first graph, this f of x, tells us to take all of these y distances and double them. So you'll see our y-intercept is now at 0, 2, and really the new graph is above the just e to the x graph. This here in red, this dashed red line there, is an e to the x graph, and you can see everything here has, like, this y distance right here has been stretched up and kind of doubled, all right, with that multiplication of 2. Whereas over here, if you take a look at our original e to the x graph, the x's have been divided in towards the y-axis. So, and even down here in this small region, things have been divided towards the x-axis. And what you get is you actually get a bigger base. It's almost like you're graphing e squared to the x, right? I mean, if that e instead was like 3, this would be 3 to the x versus 9 to the x. We know that larger base means you're steeper on the right and then below and closer to the x-axis on the left. Okay, so that's the difference between a vertical stretch and a horizontal stretch. We don't tend to do too many horizontal stretches because we can do it with just a bigger base. Okay, so we don't see that as much, but you should know it. finally, more complicated example. This here, we have the graph being shifted to the right one. So our y-intercept is over here to the right 1. It's also been flipped over the x-axis and shifted up 2 units. So this is actually going to be at the point 1, 1. And yeah, horizontal asymptote is y equals 2. And we can see the range is everything below 2. Second one, this is one that's really difficult for most students. We see this plus 3 here and we think, oh, it should end up over here on the left at negative 3. Well, the problem is that you have to first shift left 3. And then second, flip over the y-axis. So yeah, it does go to the left, but then after going to the left, being an increasing function over here, it then gets flipped over the y-axis. Boom, we end up flipped over to the right at 3, 1. And we have this decreasing exponential function. So it's just like, remember, taking that negative x plus 3, set it equal to the domain value of 0, because we used to have that y-intercept there at 0, 1. Well, what happens to that point when you solve it? You subtract 3, because it shifts over to the left 3, and then you divide by that negative, which is going to flip it over to the positive side. Okay? So those are the transformations I wanted to go over today. If you have any trouble doing any of the problems coming up, please let me know, and I will try and help you. Great. Have a good one.